We are about to start rotational motion. So this is a good time to review what we've already done and compare it to what's coming up in rotational motion. So when things move, we say they can translate, they can move in straight lines, X, Y, Z, or they can rotate. So we've been talking about translational motion up to this point. And rotational motion is what we're about to start. So let's think about each of our four lenses. First, kinematics. So the main things we were concerned with in kinematics were position, velocity, which is the rate of change of position, and acceleration, which is the rate of change of velocity. Well, with rotational motion, we are concerned with the same three things: position, velocity, rate of change of position, and acceleration, rate of change of velocity. But we're not concerned with translation, we're concerned with rotation. So how would we describe something that's rotating? How would we describe the position of something that's rotating? We'd use an angle. And if we're interested in the time rate of change of theta, that would be our angular velocity. We use omega. So we have an angle theta, we have omega, our angular velocity, and we have our angular acceleration alpha, which is the time rate of change of our angular velocity omega. Then we said we can use these definitions and derive the kinematics equations. We could derive our kinematics equations from the definitions of acceleration being the time rate of change of velocity, velocity being the time rate of change of position. We have a couple of videos back on how we did that. Because we use the same definitions for our angular variables, omega and alpha, as we used for V and A, we are going to get the exact same equations. We just replace the V's with omegas, the X's with thetas, and the A's with alphas. So everything we did with kinematics before, using kinematics equations, drawing the graphs, and getting our results through graphical approach, we can do the same thing with rotational kinematics. Let's take a look at forces and dynamics. When we looked at forces and dynamics, we basically are looking at Newton's laws. Newton's first law is inertia. And how do we measure the inertia of something? The mass. That's our quantitative measurement of inertia. Well, we have a rotational counterpart to inertia. Just like our translational inertia, it tells us how hard it is to get something moving if it's sitting at rest, or how hard it is to stop it if it's moving. We have something that tells us how hard it is to start something spinning if it's at rest, or to stop it from spinning if it's already spinning. It's a little more complicated than just the mass. It's the mass and how that mass is distributed about the axis of rotation. So for the simplest case, just a point object moving in a circle, the rotational inertia, we use the capital I for that, is equal to m times r squared. The distance from the point mass to the axis of rotation would be r, and we square that. And this is for a point mass. It gets a little more complicated for solid objects in different shapes, but for a point object, this is what it is. Then we ask ourselves, what changes the motion of an object? Right? What does it take to get something to move if it's not moving? What does it take to stop something if it is moving? Well, for something moving in a straight line, it takes a force. And for something that's spinning, what does it take to cause something to start spinning? If it's at rest, it takes a torque. We use the Greek letter tau. And that's also a vector quantity. It's not just the force acting on the object, but it's where that force is being applied with respect to the axis of rotation. It's a combination. The next question is, how are these related? Well, we look at Newton's second law. And this tells us that the net force equals ma. And for rotational motion, what do we use instead of force? We use torque. And what do we use instead of mass? We use rotational inertia I. And what do we use instead of A? We use rotational acceleration alpha. Now we want to look at our next lens, work and energy. And we said work done, in the most general case, when our force is not constant, is going to be an integral of f dot dx. Well, we can say a similar thing for rotational motion. Instead of force, we use torque, and instead of dx, we would use d theta. For our kinetic energy, when something's moving in a straight line, it has kinetic energy, energy of motion, 1/2 mv squared. And if something is spinning, it's going to have kinetic energy because all the little mass particles are moving, right? They have kinetic energy if they're moving. So we have rotational kinetic energy. I'll just put an R there, rotational kinetic energy. And that's equal to, what do you think that's going to be equal to? 1/2. What's our rotational equivalent for mass? Rotational inertia. What's our rotational equivalent for velocity? Angular velocity. 1/2 I omega squared. And our last lens is momentum. When something's moving in a straight line, it has momentum. Mass times velocity. When something is spinning, it has angular momentum. We use a capital L for angular momentum. And what do you think it's going to be equal to? The rotational counterpart for m, for inertia, is rotational inertia, I. And the rotational counterpart for velocity is angular velocity, omega. That was a nice summary of what we've learned so far with each of our 4 lenses as it applies to translational motion. And this is a sneak preview of coming attractions of how we're going to apply the 4 lenses to rotational motion problems.